Well, the first video in this VHDL in practice playlist addresses the subject of finite state machines with datapath, or FSMDs as they are also known. And the expected learning outcomes from this presentation are that you shall be able to explain what is an FSMD and what this type of circuits are used for, and also to differentiate between algorithmic state machine charts, or ASM charts, and their extension to FSMDs, which are known as ASMD charts, and to use them to specify the behavior of this type of circuits. And finally, you shall be able to translate an ASMD chart into the corresponding VHDL description. So an FSMD is actually one level of complexity above a simple finite state machine. It actually comprises a finite state machine that works as the control path. And then it comprises as well a set of regular sequential circuits like counters or shift registers, for example, that make up the so-called datapath. The control path generates the appropriate signals to specify what operations shall take place, and it receives information from the data path to decide what to do next. So FSMDs are used, as one might expect, to implement systems that are described at a higher abstraction level, and namely at the register transfer level. So we will not only handle bits and logic gates, but we will actually manipulate multi-bit words that represent the information to be exchanged among several registers. Actually, you may recall that a microprocessor may be seen as an example of an FSMD, of a complex FSMD, since in the case of a microprocessor, the data path comprises, for example, the ALU and the data registers and the program counter as well, for example, while the control path will comprise the instruction register and the instruction decoder and execution control unit, which generates the signals for all the other blocks. Well, from what has just been said, you may realize that the FSMD block diagram may be represented as shown in this slide, where the bottom part addresses the control path, made up of a finite state machine represented here using the very standard block diagram for an FSM, comprising the state register and the next state and output logic blocks. And then the data path comprises the set of data registers and the functional units that define the operations that are carried out over the information stored in the data registers. And of course we will need routing networks to convey the information to and from these various blocks in the data path. The control path receives information from the data path and external commands from the outside world to decide what to do next. Now, the ASM chart, as you might recall, was our preferred representation method to specify the behavior of finite state machines, and we will extend this representation mechanism into what is known as the ASMD charts for representing the behavior of FSMDs. Essentially, this extension consists of being able to represent register transfer level operations as well in the state box and in the conditional output boxes, whereas before, in the case of FSMs, we handled single bit signals in these two boxes. Now, you must recall that the ASM block that is represented here is the building block to represent a state, and it always comprises a so-called state box with square corners, where the Moore outputs are asserted, and then an optional network of decision boxes and conditional output boxes, which are in turn made out of rounded corner boxes. Conditional output boxes are used to represent the mealy outputs involved in the circuit, and their existence is optional, as I have just said. They may or may not exist, and actually there may be more than one decision box and more than one mealy output box. Now, to see the usage of FSMDs in practice, we will consider the example of a debouncing circuit, and at this point I do recommend that you go to chapter 5 of the book addressing the finite state machines topic, where a similar application has been presented, with the exception that there the counter that was used to set up this small delay was not controlled by the finite state machine. So since we didn't have this connection from the control path to the data path, it wasn't really an FSMD. But in this case it will be, so this can be used as an example of how to design an FSMD. Basically, the application consists of converting an irregular signal that comprises oscillation when going from 0 to 1 or from 1 to 0. This is the typical case when we use a mechanical switch, and we want to convert this signal into a clean transition output called dB level or debounced level output. For this purpose we will use a 21-bit counter, and the basic reasoning is that while we read ones and zeros during this oscillation period, the counter will continuously be restarted, and it will only happen that the clean transition takes place when the counter is restarted and no further zeros are read in the input signal, that meaning that the oscillation period has ended. Then the output will be asserted, and at the same time a debounced output tick will be generated to inform that the clean transition has taken place. In terms of the FSMD representation, we may show it as illustrated here. So we have the control path made up of the FSM, as we already know, and in this case the data path comprises simply a 21-bit counter. The 21-bit counter receives orders from the control path. In this case, the orders are simply preload to all ones, as it happens in this initial state, and also decrement, as it happens, for example, in the wait 1 state. Then the control path also receives information from the data path, and in this case the status information received consists of finding out if the outputs at the counter are all at 0. We will now analyze the ASMD chart, which is pretty straightforward to do. Actually, it has one 0 state, which corresponds to the output dB level being at 0, and one state called 1, which corresponds to the output dB level being at logic level 1. And the wait 1 and wait 0 states are simply transition states that take place while the oscillation period is taking place. So we start at the 0 state, and we ask if a 1 has been read at the input coming from the switch. If this is false, we continue to be here. Now, whenever we read a 1 at the input signal, we order the data path counter to preload to all ones and move on to the wait 1 state, where we will continue to check if this was the stable transition to 1, or if there will still be further glitches going down to 0. There are no outputs to assert, either in state 0 or 1 in what concerns Moore outputs, so the state boxes are empty in these ASM blocks. Now, while we are at state 1, we will continuously check the input coming from the switch, And if it happens that we read a 0, the whole thing will restart. So whenever we read a 0, because of a glitch, the state reverts to 0. Now, if we don't read a 0, then we will order the counter to decrement by 1 unit and then check if it has reached 0, otherwise we will continue to do this test. Now, you will notice that if a single 0 is read during this period, and this period can take like up to 20 milliseconds, if a single 0 has been read due to an existing glitch, then the whole thing restarts. It will only be when during the full period corresponding to decrementing the 21-bit counter down to 0, during that full period, if no further zeros were read at the input, then we will reach the all 0 condition at the data path counter and be able to proceed to assert the bounced output tick and to move on to state 1, where the clean output dB level goes to 1. Now the rest of the ASMD chart repeats these operations in what concerns the 1 to 0 transition, so I won't go through them in detail and leave that up to you as an exercise. It is interesting to call your attention to the fact that also in the case of FSMDs we may design the corresponding VHDL code using the explicit datapath component approach or the implicit datapath component approach. And basically, as you already know, the explicit datapath component consists of separating the datapath for the FSMD and the specifying individual sections of code for the datapath of the FSMD and for its control path. So if we separate the VHDL sections for these two blocks, then we will be using an explicit datapath approach. This may provide for an easier to understand code in what corresponds to relating the code to the architecture, but at the same time it will be slightly more cumbersome, particularly in the size of the code. And the implicit alternative consists of merging the next state logic and datapath functional units and routing all in the same VHDL code. You will see that this is the more practical approach, and that is what we will be using in practice. Actually, we will look further into this implicit datapath component approach right now. For this case, I start by calling your attention to the fact that the number of bits of the counter is defined as a constant within the architecture body, and we will have to create a user-defined type for representing the 4 states of the ASMD chart, and the 21-bit counter will have to be defined in the form of unsigned variables, since we will be decrementing this value. It cannot be of the standard logic vector data type. So going on with the implicit datapath approach, the state and data registers FSMD section follows the very standard structure that you are already familiar with. So if reset is equal to 1, then the state register will revert to the initial state and the outputs of the counter will be reset to all 0. Otherwise, if there is a rising edge at the clock, then state register will take the next state value and the outputs of the counter will take their corresponding next state value as well, which might be the all ones if we are preloading, or the current value -1. So moving on to the next state logic and datapath functional units and routing, the implicit datapath component approach enables us to provide a direct translation from the ASMD chart into the corresponding code. you see that in this case we start by the default assignments, that is to say those signals that will always be assigned this way whatever the state we are in. And then we start with the case statement that will enable us to define what is to be done for each of the four states. So we start by saying, in the case of state 0, which is the one considered in this slide, case state register is when 0, then what shall we do? We shall assert the boundary level output to 0. Well, at this point I'd like to ask you, why is this necessary? I mean, if it was to be asserted to 1, we should have written here dB level takes the value of 1. But since it is not, it takes the value of 0. But shall we have to say so explicitly? If you have doubts, you might like to read page 129 of the book, where the response to this question is given. But basically, the reason is that since we have not included this assignment into the default assignments section, we will have to say so for every state. I would consider that it would have been better to have included the dB level takes the value of 0 into the default assignments section as well, and in that case we wouldn't need to do it here. Well, after that we have a decision box where we ask if the switch input is 1, then the next state will be wait 1, and we will preload the counter to all ones. Notice that this if block does not have the expected else component, which would redirect the next state to 0 again. And so I just want to call your attention to this fact, because we will look into that in more detail for the case of wait 1. So in this case, again, we have a direct translation from the FSMD block corresponding to state wait 1 and the corresponding VHDL code. Notice that again we have to start by assigning dB level output to 0, and this would have been avoided if it was included in the default assignments section. Then we ask if switch is 1, then Qnext is decremented, and we immediately afterwards check if Qnext is now 0. Now at this point I would like to tell you that you might also consider, instead of using Qnext for this decision box, which is the one that we are looking at here now, we might have used Q_reg. And in this case, of course, we would ask if Q_reg is equal to 1, because since in that case that could correspond to Q_next being 0. Now the advantage of that is Q_next is a combinational output, so there might be occasions where we are not sure exactly at what time this output will be modified, and if that is the case, then it might be preferable to always use Q_reg for comparison purposes. Well, if this holds true, then the next state will be 1, as it says here, and the balanced output will be asserted. Now again, notice that if, on the other hand, this question does not hold true, so if it is false, it will go back to wait 1. Excuse me. It will go back to wait 1. And in this case, what will happen is that because we actually have asserted, if we go back to the to take a look at the beginning of the where is it? To take a look at the I beg your pardon. To take a look at the default assignments section, here we see that the next state has been defined by default to take the value of the current state. And since this has been defined, then we do not need to say here that if this does not hold true, sorry, we were here. If this is not hold true, then we have to go to wait 1. Well, since in this case the next state is the current state, then this has been defined by default, and so we do not need to state that state next should take the value of weight 1. Well, in what concerns the state 1, the correspondence between the VHDL code and the FSMD block is very straightforward. Once again, notice that having defined the default next state as the current state frees us from having to say that if this is false, then the next state will be 1. This has been said in the beginning. So the default assignment section really saves us quite a few lines of code. And finally, the last FSMD block again shows a similar structure to the weight 1, so I won't go into detail to explaining the correspondence between each line of code and the corresponding components in the FSMD block, but this correspondence is very straightforward, so you shouldn't have any difficulty in understanding why these lines of code have been included here. And I leave that up to you as an exercise.